Hi everyone, welcome back to the Corrosion series. In the previous video, we saw the basics and introduction of corrosion. Corrosion is basically nature's way of reminding us that metals prefer to exist in their stable, low energy forms, usually as oxides, sulfides, or chlorides. So, every time a metal surface touches air, water, or ions, electrochemical reactions start happening. It's like the metal is quietly trying to go back to its original state, and our job as engineers is to understand how and why this happens. Today, we are stepping into one of the most fascinating and honestly one of the most important topic in material science, that is theories of corrosion. If you have ever wondered why metals don't stay the way we make them, why irons rust, why silver tarnishes, or why aluminum somehow survives where other metals fails, the answer lies in these theories. In this video series, we will break down the two major theories, that is chemical corrosion, where gases directly attack the metal, and the electrochemical corrosion, where the metal practically behaves like a tiny battery and corrodes through anodic and cathodic reactions. By understanding these mechanisms, you will see corrosion not as a random problem but as a predictable process with clear scientific rules. We begin with dry corrosion, otherwise known as chemical corrosion. This is the type of corrosion that occurs without moisture. That means no water, no electrolyte, just a direct chemical attack of gases on the metal surface. Dry corrosion happens purely through chemical reactions between the metal and the environmental gases such as oxygen, chlorine, hydrogen sulfide, or sulfur dioxide or halogens. So, whenever a metal is exposed to these reactive gases, especially at high temperatures, it slowly forms oxides, sulfides, or chlorides depending on the gas involved. In simple terms, dry corrosion is the corrosion that occurs even when the environment is dry, entirely driven by the chemical combination, and the nature of the oxide film formed determines whether the metal is protected or continues to corrode. In this session, let us examine the three major forms of chemical or dry corrosion, processes that occur in the absence of moisture and are governed predominantly by the chemical nature of the metal and reacting gas or liquid metal. Our discussion will focus on oxidation corrosion, corrosion by other gases, and liquid metal corrosion, with each mechanisms illustrated using familiar real-world examples. Here comes oxidation corrosion. Oxidation corrosion refers to the direct chemical attack of oxygen on a metal surface. This can occur at room temperature for highly reactive metals such as lithium, sodium, potassium, magnesium, and it becomes pronounced at high temperatures for almost all metals, with a notable exception of noble gases such as silver, gold, and platinum, which resist oxidation due to their low chemical affinity for oxygen. A simple real life example is the formation of a dull white layer or on magnesium ribbon when exposed to air. Even without moisture, magnesium reacts aggressively with oxygen, forming magnesium oxide. Let us see the mechanism of oxidation corrosion. When a fresh metal surface comes into contact with oxygen, the outermost layer of the metal gets oxidized immediately. This results in the formation of a metal oxide scale, which acts as a barrier between the underlying metal and the environment. Now, whether corrosion continues or stops depends entirely on the nature of this oxide film. So, the nature of the oxide films are stable, protective film, unstable film, volatile oxide film, porous or non protective film. Let's get into the topics. Stable or protective film. If the oxide film is dense, tightly adherent, and non porous, it prevents further diffusion of oxygen. Aluminium is the best everyday example. Your aluminium utensils and aluminium doors or windows do not corrode easily because of aluminium oxide layer formed is exceedingly protective. Second, unstable film. In some cases, the oxide formed is chemically unstable and decomposes back into metal and oxygen. Silver and gold fall under this category. This explains why a gold ornament maintains its shine for years. It simply does not oxidize. Volatile oxide film. There are metals whose oxides are volatile at the temperature of formation. For instance, molybdenum forms molybdenum trioxide, which evaporates constantly, exposing fresh metal. This leads to rapid and continuous corrosion. And last, porous or non-protective film. In reactive metals like lithium, sodium, potassium, and magnesium, the oxide layer formed contains cracks and pores. Because oxygen can easily penetrate through these pathways, the metals continues to corrode until it is fully converted into oxide. This is why sodium metal is always stored under kerosene to prevent contact with air. And the second of the nature of the oxidation corrosion is corrosion due to other gases. Corrosion is not limited to oxygen. Many industrial gases such as sulfur dioxide, carbon dioxide, chloride, hydrogen sulfide, and fluoride can chemically attack metals. The nature of attack is governed by the chemical affinity between the metal and the gas, and whether the resulting film is protective or porous. For example, when silver reacts with chlorine gas, it forms silver chloride AgCl, which is strongly adherent and protective. This kind of film prevents further penetration of chlorine. However, if the gas metal reaction produces a film whose volume is less than the metal from which it is formed, the film becomes porous. The Pilling Bedworth rule allows us to predict this behavior quantitatively. And third nature of the oxidation corrosion is liquid metal corrosion. The third category is liquid metal corrosion, commonly encountered in high temperature system. This involves either dissolution of the solid metal into the liquid metal or penetration of liquid metal into the grain boundaries of the solid metal. A very important real world example comes from the nuclear reactors where sodium metal is used as a coolant. However, sodium chemically attacks cadmium, leading to corrosion of reactor component. This phenomenon must be carefully controlled for safe reactor operation. Here comes the end of the video. Let's summarize. Chemical corrosion may occur through oxidation, through reaction with other gases, or through attack by liquid metals. The key controlling factors in each case is the nature of the corrosion product, whether it is stable, porous, volatile, or protective. Understanding these mechanisms is essential when selecting materials for industry reactors, pipelines, heat exchangers, and even household appliances. Corrosion isn't magic, it follows rules. And once we understand the rules, we can control the outcome. Thank you for listening.